Yeah, our last speaker today is Greg Smith, and he'll be telling us about the discriminant locus of a vector bundle.
Thank you very much, Jack. First, let me thank the organizers, Jack and Louise, for inviting me to participate in this session. I've enjoyed the talk so far today, and I'm sure Monday will be equally as good. This is based on joint work with Hiro Abo and Robert Lazarsfeld. Our contribution will appear at the end, and it's a sort of ongoing thing, so it's conceivable the final document will look a little different than I represent it today. Oh, let me say one other thing. Like several other people have mentioned, it would have been a lot more fun to actually be in Argentina today. I understand that's not possible for a variety of reasons, but maybe we'll all get there together at some point in the not so distant future, which would be a lot of fun. So my talk does have some differential operators looking in the background, but they're not going to be quite as front and center as some of the other talks. But there will be lots of algebraic geometry, even some commutative algebra. So I think it does fit in with the theme of the session. So today we're going to fix capital X to be an n-dimensional smooth complex projective variety. The projectivity is important. Variety, I mean reduced and irreducible. Complex numbers is mostly for convenience, although algebraically closed and characteristic zero are implicit in several steps I do along the way, and we're taking lots of derivatives. So in characteristic P, I would assume there would be some other issues arising. Really the object of interest is going to be capital E, a globally generated vector bundle on our variety X. So of course, using the tricks that algebraic geometers always do, I'm thinking of this as a locally free coherent sheaf. And I'm going to assume throughout that it's of low rank, by which I mean its rank is less than or equal to the dimension of the underlying variety. Okay, so that's just a minor assumption. We'll see how it's convenient. The definition that gets our central player is the discriminant of this vector bundle. And so first, let's think if we have a global section, we say it's non-singular if the zero scheme of that section, i.e. all the points on our variety X where this section vanishes, is non-singular of codimension E. Okay, so there's two parts to that. So the choice of a section, remember, it's locally free, so I may as well think of it as, at least locally, is given by a direct sum of line bundles. So that's an interesting case. And then your section is really a tuple, an E tuple of sections, and saying it's non-singular, we're taking the intersection, right? There's going to be divisors or hypersurfaces associated to each component, and we're intersecting all of those. So that could be singular, that wouldn't surprise us. But the codimension is very important here. It's certainly possible that for a given section, you'd get the wrong codimension. So the non-singular involves really two parts, it being a smooth scheme and having the right codimension. And so it could sort of fail for either reason. But if it does fail, then we call it singular, of course. And so the discriminant loci, or just the discriminant of this vector bundle, is the locus in the big projective space generated by the global sections of our guy. The star shows up there because I think of projective spacing as quotient bundles, not as subbundles, but okay, minor technical issues, of the singular sections. So I take the singular ones, give us the discriminant. And so this is a scheme. In fact, it comes with a natural scheme structure, right? The zero sections come with a scheme structure. This is really a scheme in this projective space. And so there's a variety of natural questions one asks when, in fact, typically has discriminant type objects showing up. Is this thing irreducible? Is this scheme a hypersurface? Sort of begs the question. It turns out it's frequently going to be a hypersurface. That's, again, maybe not surprising to those who studied discriminants in any other setting. And assuming it's a hypersurface, we would, of course, like to know its degree. right? It's cut out by some homogeneous polynomial. What is the degree of that polynomial? And we'd like to phrase all of these, have answers to all of these questions as generally as possible, and ideally phrase them in terms of natural invariance or properties of the vector bundle E. Okay, so that's the setup. It has a geometric reinterpretation, which connects it to a larger body of work and maybe makes the question seem more natural. I think from a vector bundle point of view, it is natural, but you might, if you haven't thought about vector bundles, you wouldn't, I think of this question initially. If we can take a more geometric point of view, we take our vector bundle and we make a projective variety over it with a map to X. So P of E is the projective bundle, really thought of as a variety or scheme. We can construct it as the product of the symmetric algebra, but I won't need that technology. But it's really a geometric object, a space over X. It comes with a natural projection map to X. And as a projectivized bundle, it also comes with a tautological line bundle, O of 1, right, given by, well, lines, one-dimensional quotients on this guy. So every projective space comes with a tautological line bundle. This guy does too. The amusing thing is that the global sections of this tautological line bundle L are canonically isomorphic to the global sections of our vector bundle E. So we can transfer questions about E to L. And this is a long-standing tradition. I think certainly in terms of positivity for vector bundles, the classic thing to do is to define the positivity property for a vector bundle by first knowing what it is for a line bundle and having that property for this canonically associated L. So in particular, the now standard definition, I think originally due to Robin Hartshorne in this way, is we say the vector bundle E on X is very ample if the line bundle L on P of E is very ample. So we transfer our notion of very ampleness from line bundles, which we understand, to vector bundles using this construction. And so when E is very ample, that means P of E embeds into the projective space we were interested in. Then the discriminant of E is isomorphic to the dual variety of this variety P of E, where P of E is embedded into this projective space by the complete linear series associated to our line bundle. So understanding dual varieties is, again, a classical and well-studied thing to do. And understanding this discriminant then becomes a special case of this more general problem of understanding dual varieties for a particular class of varieties, those which are projectivizations of some vector bundle. Right? And so the understanding dual varieties, the three questions I had before, right? When is the dual variety irreducible? When is the dual variety a hypersurface? When it's a hypersurface, what is its degree? Are some of the natural questions that one asks for dual varieties, and that's now sort of fits in this context very nicely. So vector bundles with degenerate discriminants corresponds to projective bundles with small dual varieties. So we get this correspondence or transfer, and I think it maybe inspires more interest in this question if you weren't just interested in the original version. We have this geometric setting. It also suggests some tools for attacking or getting a handle on these guys. Okay. So maybe an example to show you that things can be a little complicated. It's not entirely trivial. Also gives you a sense that one can, at least in principle, compute these things in Macaulay 2. In fact, this example was literally computed in Macaulay 2. Well, it can become computationally challenging if you have a lot of variables. If you're in a big projective space and have a lot of variables, you're not so likely to actually have primary decomposition or any sort of calculation finish in, well, the time I'm willing to devote to it. But in principle, you can do these things algorithmically. So the example I'm going to look at is just on projective space, projective plane, P2. And I'll choose as my variables x0, x1, x2, as many people would. And I consider this map between direct sums of line bundles given by a 3 by 5 matrix. It happens to have just monomial entries up to a sign, so not so complicated. And the image of this thing is a vector bundle. So the image, one has to actually check that. It's not free that if I write down any matrix that its image is going to be a vector bundle. One has to actually check that it's locally free, and one can do that calculation without too much effort. Moreover, it's cooked up this way so that the global sections of this vector bundle, which is the image of this map, can be identified with the columns of this matrix. So the vector space of global sections is a 5-dimensional vector space, which I identify with the columns here. And again, it's not hard to unpackage that in any way. The nice thing about that is I have now explicit coordinates chosen on my global space of global sections, so I can actually work out the equations for the discriminant of this guy. And so if we choose the U naught up to U4 to be those guys, and we compute the appropriate matrix and analyze it and do the primary decomposition of Macaulay 2, you see that the ideal that cuts out the discriminant is not irreducible. It's got 2 components, and it's certainly not equidimensional, and life is complicated. It's not irreducible. It's not a hypersurface. It's so it's certainly not difficult to generate examples like this. This is a pretty tactile one that we can get our hands on and see that life can be a little complicated. So it's certainly not always the case that we get even something that's irreducible. And it's sort of typical that we get some lower dimensional components that are, in some sense, the part we're not interested in. Okay. So we're not the first to ask these sort of questions. In fact, there's a reasonably large literature of which I'm slowly getting myself familiar with. I must say I may not know all of the points in the literature yet, but this in this context, there's I'm just selecting a few highlights. And from the point of view, the way I've set it up, this first result to Latirini and Muniz, I'm not sure I can pronounce their names very well. So they stick to this special case, which turns out to be a particularly interesting case where the rank of the vector bundle is equal to the dimension. And we'll assume it's very ample. And then you can ask, is the codimension of our discriminant loci bigger than 1? Does it fail to be a hypersurface? And it's in fact true if this degree of this particular class here, right, we get this somewhat involved in expression, right? So these are the Chern classes of our vector bundles, the first Chern class, the top Chern class, and the one from the top Chern classes of our vector bundle. Kx is the canonical bundle, the exterior power of the sheaf of differentials. And so this gives us a class, and we ask what the degree of that class is, and it has to have degree 0. This expression actually is also equal to the Chern class, a particular Chern class of the first jet bundles of L. So there, you couldn't rephrase it. In fact, they do rephrase it in terms of jet bundles. So there are some differential guys lurking around. So we get an explicit test for that, which is quite nice. But in fact, this test is even better. It allows you to classify the ones where it's defective, right? When you have codimension being the wrong size. And you can get that really in one special case when you're on projective space and your vector bundle is a direct sum of twists of O of 1. That somehow the degenerate one and all the other ones fail to be degenerate. And moreover, when it is a hypersurface, which is frequently occurs, its degree is given by this degree class. This class which tested whether it was going to be a hypersurface or not does actually give you the honest degree in this case. So we're able to answer when the rank is equal to dimension. I've given pretty good answers to all 3 of the questions. When is it irreducible? sorry, I guess I bypass the irreducibility. When is it a hypersurface and what is the degree? And so that's a pretty nice situation. And so you might say, well, what did we contribute? What are we doing here? Well, our approach is to attack these examples and a few other related things with a new proof technique. So really our contribution is to attack these things in a different way, a way that turns out to be, we think, concise and clean and parallels some other constructions, particularly in the work of Rob Lazarsfeld. So how do we do it? We use this technique, I would say, that's I learned from work of Green and Lazarsfeld and has been widely used by many other people studying vector bundles. And that's to consider the kernel bundle. So E was by definition or by assumption globally generated. So that means I get a surjective map here, right? If I take the global sections and map on there just the natural evaluation map, that's going to be surjective, and I declare M to be the kernel. And it's often called M. Lazarsfeld actually explained to me when he was first studying it, they thought of it as analogous to the normal bundle. It's not a normal bundle, but it reminded them of a normal bundle that was N. So they used M because that was the adjacent letter in the alphabet, and it's almost always called M. These kernel bundles in the literature. So once we have this bundle, we can construct. Well, we can take the projective space of the dual. And we actually have a concrete interpretation of that thing as incidence pairing. It's really pairs of points on our variety in sections such that when we evaluate the section at the point, we get 0. So, I mean, we have an algebraic definition of how to projectivize a bundle as a proj or something, but here it has an explicit reinterpretation as an intersection pairing. And so in particular, we can think of it as living inside this product, X cross our big projective space. Because it's sitting inside this product, there are two projection maps, the usual incidence correspondence things. We could project onto X, or we could project onto the big projective space. And so I'll let Q be the projection onto the big projective space. That's going to be the interesting map for us, or the most interesting map. So this is the restriction of the projection map onto the second factor. And so we talk about the ramification locus of this map, which is really the Arth degeneracy locus of the differential. So we can pull the differential, the differentials on the target space back to P of M star and have a map to the differentials on P of M star. This is an explicit map of vector bundles. And so talk about the degeneracy loci of this guy. You take the appropriate minors if you choose a basis of the matrix in question. And so this we think of as a ramification locus. And the key insight is, well, this thing can have, this comes with the natural scheme structure, and it can have embedded complicated scheme structures, absolutely in examples. But if you take the underlying reduced scheme, and take the image of it under Q, that is the discriminant. So the effort goes in, that part is almost formal nonsense. The effort in getting the hypothesis to come out is to show that the ramification locus is reduced in the situations that we have those hypotheses. So that's where a little bit of effort goes in. It's not so bad. And so we get at we get the results like I highlighted before, and several more in that flavor. The fun part, I guess, is this technique also leads to a quick proof of other results about vector bundles, in particular, the Bogomolov instability theorem for rank 2 bundles on algebraic surfaces, another celebrated result. So the novelty is this approach. Looking at this ramification divisor locus quickly produces or recovers several different related results, which is fun. I'm out of time, so I'll stop here.
All right, thank you. Are there any questions for Greg? I had one that might be kind of simple, but maybe I'm missing something. So in this theorem, you end up with this classification where the only things of where the only irreducible discriminant loci of smaller dimension come from PN projector
No, it's
space.
the other way around.
Oh, okay.
Yeah, so the PN one is the one that behaves poorly. All the other ones, you get nice irreducible things that are hypersurfaces.
Oh, right. Okay. Okay. Well, what is it about PN, or what characterization of PN is sort of going into this?
You just do the calculation in some sense in that case, and you end up showing that the image lies inside the generic minors of a matrix, so it has the wrong codimension. Is really what happens in the direct sum of O of ones on PN. So it's for codimension reasons it fails there, and it's just somehow too small, too degenerate. I don't have any deeper way of that, right?
I see.
The space of counterexamples is small, right? The phrase I've heard is you have the law of large numbers and the lawlessness of small numbers. This is in the lawlessness end of the spectrum.
I see.
Things coincide, and there's a little bit of, they can because there's enough space.
I see. Okay, thanks.
I have a question.
Certainly.
In the case of the theorem about hypersurface and having known the degree, can you say something about if it's irreducible?
Yeah.
Oh, so in the hypersurface case, it is irreducible. Yes. So when we know the degree, we are saying it's irreducible. Yeah. So we know about the irreducibility in the hypersurface case. Sorry, I didn't make that clear. Yeah.
And smooth. So this is
I guess I don't know about smoothness off the top of my head, but that I didn't ask the question. Our techniques probably say something in that direction, but I don't know off the top of my head.
Thank you.
I think this should be a difficult question.
The smoothness? Okay.
Yeah, because somehow it amounts to consider the singularities of delta E, right? Yeah, I think even in the toric case, and you take sum of line bundles or just one line bundle, it's a very difficult question.
Okay.
To understand which are the singularities of the discriminant. And in that case,
that's certainly, that's a certainly more delicate question. I was just thinking of something easier. Could we tell when it was singular or not singular? But to actually describe the singularities is going to be a lot more delicate. Absolutely, which would be great to do. But our techniques are not. I'm not optimistic we're going to shed any light in that direction.
Hi, I have probably not so related question, but is there any relation between these nice vector bundles where the discriminant is nice and I don't know, ACM bundles or Ulrich bundles? Maybe like.
Yeah, none that I know of. Not that I know of.
Okay, thank you.
I also have one question.
Certainly.
Is it possible to say something in the higher codimension case? For instance, if it's complete intersection, like
excellent question. Our techniques don't shed any light on that, but that's an interesting question. Absolutely. Yeah. Somehow the incidence correspondence doesn't see that so well. But I like the question.
But there are no works on that, right?
Oh, no, I don't claim that. The literature is large, and many special cases for even special bundles have been studied at great length. And I don't claim to know, I'm just not an expert in the literature to know that, yeah, I like just the opposite. I would be surprised if there wasn't some special bundle where somebody had analyzed it, but I can't point you to a precise reference.
Okay, thank you.
Are there any more questions?
Oh, yes, probably also unrelated. Recently, I saw a talk of you where you characterize a smooth Hilbert schemes. So for this, I mean, you're taking locally free things like copies of line bundles in a sense. Do you think that your techniques, you could classify quote schemes of vector bundles when they are smooth?
So that's really not related to this talk, but I think there should be a theory of when you can analyze smooth quote schemes. Yes, I think for bundle, you know, for at least for quotients of direct sums of line bundles on projective space, probably have to at least initially stick to projective space. I would think that one should be able to analyze when quote schemes are smooth. My intuition is it's going to be even rarer than the usual Hilbert schemes. So the number of examples is going to be small, but so I would be optimistic that there is that is tractable. I haven't actually tried to make any headway yet in trying to do that, but yeah, if you end up doing even computing some examples, I would be keen to hear about it. Yeah, that would be fun.
Thank you.
Any other questions? Well, if not, let's thank Greg again.